best compound to store the energy is octane.
We have a better solution. Hello everyone, a few seconds ago, you have heard about the scenario of the case study 2. In this 10 minutes video, I, Alex, and together with my colleagues will present to you our solution, which is better. Without further ado, let's begin. For this case, we are using the first law and second law of thermodynamics. The first law of thermodynamics states that the total energy in the universe is constant. It means that it can neither be created nor destroyed, but it can be converted from one form to another. As for the second law of thermodynamics, it stated that the entropy of the universe increases in any spontaneous process. Based on this law, we discovered the flow of the conversion of energy. Starting from step 1, we convert the solar energy into electrical energy. Then step 2, the electrical energy is sent to the energy storage system, ESS, to be used to do step 3, where electrical energy is converted to chemical energy stored in the chemical compound that we will propose based on several criteria. Next, step 4, the chemical will be transported to the city, and finally, the last step, it can be used to regenerate electricity at night. A spontaneous reaction is preferable to produce the chemical compounds so that it is easy to be produced. Whew, it's quite long for the intro. Now, what is our objectives and problem statement, Nabila?
Experiment, we are going to determine 3 suitable compounds that can be used to store electrical energy in order to replace octane. But now, the most crucial problem is, what is the most suitable compound to store the electrical energy among all the compounds suggested?
She's asking the questions and we're giving the answers.
Yeah, so we have picked 3 substances to run our trials against octane, which is pentane, nonane, and metal ester, and we will compare them with 5 significant criteria. So the first criteria is based on their heat of combustion. Data shown that octane has negative 5,470 kJ per mole. Compared to the octane, nonane has higher amount heat of combustion, while pentane and metal ester is lower than octane. A higher heat of combustion is so important as the compound can store more energy. The next criteria is the state of matter. In the room temperature, octane is in liquid form, as well as metal ester, pentane, and nonane. Liquid form is the most preferable compound because it is easy to extract and transport over long distance to the residential area, which is our main aim. Hence, liquid fuels are better as they are cheaper than solid fuels. Not only that, we also consider the specific heat energy of the compound. A high specific heat energy of compound is better because the higher the specific heat energy, the more energy can be stored. Based on our research, octane has 47 megajoule kg/K. Compared to the octane value, nonane has similar value with octane, while pentane and metal ester has lower value.
Through our research, we were able to compare the substances based on their energy density, with nonane having the highest energy density and pentane having the lowest. Octane is actually placed second highest in order of increasing energy density. Having a higher energy per volume is important so that a small amount of fuel is enough to power systems for a long time. We also compared the substances based on their abundance in source. From here, we can see that metal ester biodiesel can be sourced from palm oil waste and also palm oil plantation, whereas octane, nonane, and pentane comes from the fractional distillation of petroleum deriving from crude oil. Both sources are abundant in Malaysia, but since metal ester biodiesel has a very low energy density, it will take larger amount of palm oil plantations to meet the higher demands of fuel, hence promoting deforestation in Malaysia. Therefore, to prove our findings, we proposed an experiment.
To gather appropriate data, firstly, took 100 grams of water. After that, methyl ester in a burner was used to heat 100 grams of water. Next, measure the temperature change for the water. Then, the mass of burned methyl ester was measured by measuring the change in the mass of burner. After that, the heat absorbed by the water was calculated. Next, amount of heat per gram of burned methyl ester was calculated. And finally, the experiment was repeated by replacing methyl ester with pentane and nonane.
After conducting the experiment, we can tabulate our data in this following table. For the mass of water, we fix the mass of water for each straw to be heated as 100 gram. By using the proposed compound such as methyl ester, pentane, and nonane, The compound is used to heat up the temperature of water by 20 degrees Celsius. To find the heat energy absorbed by the water, we can calculate the heat energy by using the formula Q equals to mc delta T, such that m is the mass of water, C is the specific heat of water, which is 4.2 joule per gram per degree Celsius, and delta T is the change in temperature. To calculate the heat of combustion, we can use the heat energy release and divide it using the number of mole of compound. To find the number of mole of compound, we can use the mass of fuel burned and then divide it using the molar mass of the compound for each trial.
For the data analyzing, the data and calculation were constructed to calculate heat of combustion for each compound. First, pentane. The heat release is negative 8,400 joule, calculated using Q equal to mc delta T. Assuming the mass of fuel burn is 0.172 gram, we calculate the mole of pentane by divide mass to molar mass, where molar mass for pentane is 2.38 power of 10 negative 3 mole. Lastly, we calculate the heat of combustion of pentane is equal to negative 3,529.4 kilojoule per mole. Second, nonane. The heat release is negative 8,400 joule, calculated using Q equal to mc delta T. Assuming the mass of fuel burn is 0.137 gram, we calculate the moles of nonane by divide mass to molar mass, where molar mass for nonane is 1.367 power of 10 negative 3 mole. Lastly, we'll calculate the heat of combustion of nonane equal to negative 6,144.8 kilojoule per mole. Lastly, methyl ester. The heat release is negative 8,400 joule, calculated using Q equal to mc delta T. Assuming the mass of fuel burn is 0.240 gram, we calculate the moles of methyl ester by divide mass to molar mass, where molar mass for methyl ester equal to 8.29 power of 10 negative 4 mole. Lastly, we calculate the heat of combustion of methyl ester equal to negative 10.132 kilojoule per mole. But for methyl ester, the mass we predict is too high, thus we use the ratio. From the calculation, nonane has the biggest value of heat of combustion.
In this experiment, heat energy was released from these three fuels. Therefore, the reaction is exothermic, thus delta H is negative. The combustion of these fuels has an increase in entropy as the liquid fuel reacts and releases gas products, that is carbon dioxide and water in vapor form. The delta S is positive. As all compounds occur at elevated temperature, the T is positive. The Gibbs free energy for all these three compounds are shown at the table below.
In conclusion, there are three compounds that can replace octane in storing energy, and the best of them is nonane because it has the highest heat combustion, high spontaneity, high specific heat capacity, and high abundance. So, what's your opinion, Mr. Best Engineer?
Alright, I give up. Your solutions are better than mine.